Okay, hi class. This section here that we're looking at, the yield of a chemical reaction. There's a lot of really good examples that you can find in this section to help you with your STSC assignments. Probably every question you look at almost has a chemical reaction that's used in industry. Between this section and the last Chemistry and Technology 5.7, there's some really good examples of chemical reactions that chemists and chemical engineers use. And one of the really important things in chemical reactions, especially when it involves industry, is what's called the yield of a chemical reaction. We're concerned with maximizing the amount of product because it's being used for sale. Profit is important. Environmental factors are important. Energy costs are increasing all the time, so the amount of money spent to actually make the reaction go is an important consideration. So anything that can be done to get the most product for the least amount of expenditure is really important, as well as the amount of chemicals that are used to produce it are all things that need to be considered when working in industry. So we generally call the amount obtained from a chemical reaction the yield. We look at usually the yield would be something that's measured in a mass or a volume. The units are particularly important. They would vary quite a bit depending on the scale. It could be a micro scale reaction, or it could be on a very, very large scale where megatons are produced. Nonetheless, we look at the amount of product that obtained from calculations. We've been doing lots of those in the last week or so. And whenever we produce a chemical in a chemical reaction, we can do theoretical calculations, and this would give what's called the theoretical yield. So the theoretical yield is just a number, and at some point it has to be verified. The amount that we obtain as measured from the end of a procedure is called the actual yield. Okay, so pretty easy to tell from the names what we're referring to here. When we take those two values and compare them, we would be looking at the efficiency of a chemical reaction. Be a little bit like looking at how much energy it takes to power a light bulb and how much light we actually get from that. Efficiency is, in this case, not so much matter in compared to matter out, but rather it's a comparison of what we expected by the theoretical yield as a maximum possible amount and what we actually got from the experiment, the actual yield. So this is how we describe the efficiency of a chemical reaction. And when we do that, we're usually looking at calculating the efficiency as a percentage, and we call that the percentage yield. So that's what percentage yield refers to. It's a ratio converted into a percent comparing the actual and theoretical yields. And so we would quantify it as follows. Percentage yield, there's no particular symbol that we use, so we're not introducing a new symbol here. It will have units of percent, and that would be a ratio of the actual yield, which can never be more than the theoretical yield. At the most, they would be equal, and rarely would that ever be the case. And we divide by the expected yield or the theoretical yield, and we multiply it by 100, and then that result will be in a percent. Okay. It's important when we go and look at these chemical reactions, we recognize that there are a lot of things that can be done in chemical engineering to optimize the yield of a reaction. There are factors which limit or reduce the yield. And here, we're not talking about limiting reagents so much. We're referring to factors which just cause the amount of product to be limited or reduced. And there's actions that can be taken to minimize loss or low yield. One of the first things that we need to consider when we look at chemical yield in a reaction would be the experimental procedure. All right, so that's one of the key factors here which we want to consider is how is the experiment being done, what kind of equipment is being used, and anything where people are going to be handling the chemical or equipment is being used to pour or transfer. That's a major factor which can limit the yield. So experimental procedures. Actions that can be taken to minimize loss would be things such as obviously caution and care. We can take in transferring, handling, and cleaning equipment. Okay, that can all be useful in making sure that nothing that the experimenter does is going to minimize the yield. Second thing that can be looked at when we consider percentage yield is purity. Okay, reagent purity is a huge factor, and in industry we always seek to use the most pure starting materials. So action to minimize loss here or low yield would be use of high purity reactants, and avoid contamination, which also can be affected by the cleanliness of our equipment. Okay, a third factor, which is not always obvious, but would be byproducts or side reactions. So these would be reactions that don't produce the desired product, and as a result, they can contaminate the final product, or it'd be difficult to separate out the products from each other, or this could be costly. So the action to minimize the loss would be, in this case, be aware of all possible chemical reactions. And probably be prepared to separate out byproducts. So it's not so bad if the byproducts are formed, and in some cases the byproducts could actually be beneficial or useful in industry. Maybe they can be separated and sold to another factory, another chemical industry could use those. And the last factor which limits the yield would be the reaction conditions. And in this case, not being aware of the necessary temperature or pressure, or maybe it's the form of the material reactants that you need, could really reduce your yield. So reaction conditions might be really important here, and again, the action to minimize loss of yield there in this case would be adapt the reaction, or adapt slash engineer the conditions to suit the best possible yield, and that could be temperature, pressure, maybe the presence of catalysts are important. It could be reaction time, either waiting longer or maybe getting the product out sooner before other byproducts are formed that can contaminate the main product. So these are all described in your textbook on page 238 in more detail. Right? You've been given student worksheet 5.6a. these practice questions here are solved, and the solutions, at least the answers, you can check on the website on this slide here. Solutions 4, 5.6a. So I'll leave those two questions for you to try on your own. I'm going to have a look right now at a couple questions from section 5.6, and the first one deals with chemical reaction that produces iron. This is the purification of iron from iron ore. And one of the things I thought would just be interesting to see is this heating process uses something called a blast furnace. So I'm just going to show a little clip here that kind of focuses on that technology. Let's have a look.
The modern blast furnace consists of a giant stack lined with fire brick. Iron ore, usually in the form of iron 3 oxide, is continuously fed into the top of the stack along with coke and limestone. As the material moves down the stack, a blast of preheated air at 1,000 degrees Celsius rises through the stack, burning the coke to form carbon dioxide and heat. The heat decomposes the limestone into calcium oxide and additional carbon dioxide. The carbon dioxide oxidizes coke to form carbon monoxide, which in turn reduces the iron ore to iron. The molten iron is tapped into large ladles holding hundreds of tons at the bottom of the furnace. Waste materials in the form of slag are removed from the top of the furnace and disposed of in large pits.
Okay, so that was a good look at the blast furnace, which is used in this chemical reaction. The overall reaction here, there was multiple steps, as you saw. And this is something that I think you want to start appreciating in chemistry, is that when write an overall reaction equation, it's quite often the sum of a bunch of steps put together. And even the coefficients that we use in this overall reaction equation, and we balance it, and we think we're so confident that that's exactly how the chemicals combine, quite often are a combination of a bunch of steps in which that reactant or product appears. And you'll appreciate that a little bit more if you go on and you take the 4U chemistry as well when we look at reaction mechanism. But in this case, the end result is we get iron, carbon dioxide, produced by heating this hematite ore, which is the iron 3 oxide in the presence of carbon monoxide, which was produced as the coke got oxidized from that hot gas coming up, the hot air. And so the carbon monoxide plus Fe2O3 goes to CO2 gas and iron, which was molten, so it'd be liquid. So if we're to balance that, that's the first step in this process before we can go through the stoichiometry. We're trying to determine, starting with 635 kilograms of the iron as an outcome, beginning with 1,000 kilograms of the hematite, the mass of the ore is this, and then we have the mass of the iron is 635. So those you should now be connecting with yield, as in this is the actual yield. Okay, and then this is a limiting reagent. Okay, it's not a yield, but it's a limiting reagent as a starting amount. Carbon monoxide was not in short supply there, and there was lots of calcium carbonate present to be able to produce more and more and more of carbon monoxide, so that all of the iron 3 oxide could be reduced to its elemental state. So we don't have, in this case, the percentage yield directly from those two numbers. What we need to know is what was the theoretical yield. The theoretical yield is not known. So that's important to identify, is that the theoretical yield has to be determined from a theoretical calculation from our limiting reagent. So we're told that the limiting reagent is the hematite. So the theoretical yield still has to be determined. So at this point, let's balance the reaction equation. The balanced reaction equation is provided on page 240, but here we have 3 oxygen atoms on the left side, plus 1 more, but only 2 on the right side. So if we're trying to balance oxygen, we do have an even number of oxygen atoms on the left side, but we have more. So here, rather than making, I want to say, the mistake of changing the coefficient of carbon dioxide to 2, which causes the problem of unbalance in the carbon, we can kind of, with a little bit of foresight here, make the coefficient on the carbon monoxide 3 to bring up the number of oxygen atoms to 6. Coefficient on the carbon dioxide has to be the same as the coefficient on CO. And here now we have the ability to balance the oxygen and the carbon at the same time. And then iron as an element can be balanced last. So it's a 3 to 1 to 3 to 2 balanced reaction equation ratio here for the moles of reactants and products. We can now take the limiting reagent, and we don't need to determine the amount of excess reagent here. We're just looking at converting that mass of iron 3 oxide into moles, and then compare that to the moles of the iron as a product, and then we can look at the theoretical yield. So that would involve the following steps. Okay, knowing that molar mass is in grams per mole, I'm going to convert the masses of the limiting reagent and the actual yield into grams. So you need to know that there is 1,000 grams in 1 kilogram, or 10 to the 3 grams per 1 kilogram. So we're going to be multiplying by a factor of 10 to the 3. Now I used 4 significant digits in 1,000. I just thought that that would make the precision of the question a little bit more meaningful, so I took 4 significant digits, taking that 1,000 as exactly 1,000, so 1.000 by 10 to the 6 grams. Mass divided by molar mass is the first step. The molar mass of iron 3 oxide is 159.70 grams per mole. That gets divided into the million grams of limiting reagent. That produces a molar amount of 6.261 by 10 to the 3. I just carried 1 significant digit extra at this point. So I'm limiting my answer by 4 all the way through here. I'll remember that. The molar ratio between the iron 3 oxide and the iron is 1 to 2. So I'm doubling the number of units of iron compared to the units of iron 3 oxide. So I double that value. And the last step, in step 3, is taking the number of moles and multiplying by the molar mass of the element at 55.85 produces 6.9943 by 10 to the 5 grams. So it's almost a million grams there. So we start with a million grams and we get, 700,000. Okay. So that's a mass ratio, but we at the most could have produced this is the theoretical yield calculation based on 100% conversion of every single kilogram of that hematite ore. The most we could have produced is the theoretical yield. So I hope I've made it clear at this point that theoretical yield is also maximum yield. That's really important, maximum yield. Now, with that, the calculation of percentage yield is fairly simple. We have percentage yield being equal to the ratio of the actual divided by the theoretical, or maximum, by 100. So that would be the actual being 6.35 by 10 to the 5. That's the 635,000 grams as actual divided by a 6.9943 by 10 to the 5 maximum theoretical. We'll get a percentage yield at 90.8%. Approximately. Okay, so I've rounded there to 3 significant digits. And that's the percentage yield. Okay, looking at number 10 on page 243. The answers are in the right margin here. I've just modified the question a little bit. I think when you're looking at a question like this, you kind of need to know the the steps that are going to get you from the beginning to the end. It's great if you can calculate percentage yield, you understand actual and theoretical and how they're different. But when you're faced with a question like this, you need to sort of read the question really carefully a few times and just start to look at, okay, what information am I provided with? I know that I have some chemistry going on here. I'll show this video clip in class called Copper Ore to More. It's interesting. It shows how copper, pure copper is produced from its ore. In this video, I just want to show the steps. Once we've got those steps, you can carry them out and then compare your answers to what's found in the textbook just to confirm that you're on the right track. But here, we're told that so much oxide of the copper 1 oxide is reacted with so much of the sulfide. So those are the reactants. We need to really kind of try to highlight, okay, what information we're getting. In this case, so much metal is produced. So it's obviously for the production of copper. So the metal is the copper, and we're being asked to find the percentage yield. So in this case, one of the first steps is determine overall reaction equation, okay, and balance it. So we're going to do that. We get some practice with writing balanced reaction equations. Now, in the textbook, it's shown for you. So that's obviously not going to require much more than just copying it out. So we have the 2 copper 1 oxide relative to 1 unit of copper 1 sulfide, producing 6 moles of copper in its elemental state, and then sulfur dioxide gas. So balanced reaction equation is step 1. Now, since we're given masses of the oxide at 250 grams, kilograms rather, masses of the sulfide at 129 kilograms. This is a type B limiting excess reagent question. We don't know which of these two is going to be completely consumed. We can write down the amount of metal that we produce. As a result, we get 285 kilograms. That's the mass of the metal. And of course, that is our actual yield. Okay. So what we're dealing with here is write down the information with the balanced reaction equation. In step 2, what I would do next is determine the limiting reagent. Now this is easier said than done. Determining the limiting reagent, this is a good review question, involves really several things. It requires moles of copper 2 oxide or copper 1 oxide. It requires moles of copper 1 sulfide. Both of those have to be determined from moles equals mass over molar mass. We then have to know the mole ratio of copper 1 oxide to copper 1 sulfide. In this case is 2 to 1. So we have to use that, and that has to be sort of a available versus needed comparison. Once the limiting reagent is determined, then we're going to be moving on to step 3. Stoichiometry takes over here, and then step 3 we're going to be looking at determine the number of moles of copper. In that case, that would be using moles of copper equals either 6 times the number of moles of copper 1 sulfide, or moles of copper equals 3 times the number of moles of copper 1 oxide. Question is, we don't know which of those 2 mole ratios we're going to need. That requires step 2 to be completed first. So first the limiting reagent is determined, and that will either be the amount of this or the amount of that. So that's really important that step 2 has to happen. Once the number of moles of copper are produced, then step 4 would be convert to a mass of copper, which would be the theoretical yield. And of course, that would require using mass equals moles times molar mass, and then step 4, part B, if you want to say there's only 4 steps, it would be calculate percentage yield. Okay. And we've done that in the previous question. So you need to be able to go through all these steps and make sure you know how to do all the things in them. This is a type of question that on a test, this can really challenge some students. If you haven't had enough practice, you need to know your stoichiometry all the way through, and you need to be able to understand the big picture. So writing out your steps and sort of planning these questions with groups in class will be really helpful for you to be prepared for the overall unit test with questions like this. Okay, so lastly, just a reminder that this student worksheet question, I'm not going to go through either of those 2 questions on the video. You can ask me in class if you're needing extra practice, you want to check your answers there, please ask me. Just referring back to this note, which we completed at this point, those are the assigned questions with group work and then also independently. Okay, we'll see you tomorrow.